Next, I'm going to discuss an out-of-order processor. This is one of the biggest innovations made more than 20 years ago, which is used in nearly every high-performance processor today. And this is essentially a hardware-intensive technique that tries to maximize the level of parallelism within a program and tries to maximize the resulting IPC. Okay, so I'm going to start with this figure, and this basically lays out what an out-of-order processor looks like, what different components it has, and I'll step through what is being done in each stage. Okay, so to start things off, you of course have your branch prediction and instruction fetch unit, right? So that does not change. So instructions are usually fetched in the expected program order, right? So when you're fetching instructions, you may not know which way some branches are going to go. You make your best guess based on some sophisticated branch predictor, and you start fetching those instructions. Okay, those instructions are then placed in an instruction fetch queue. Okay, so this is just a buffer that keeps track of everything that you have fetched so far. Okay, and this is a buffer that typically may have say 16 to 32 entries. And what it tries to do is it tries to buffer a whole bunch of instructions so that even if you have a cache miss, you still have some instructions that you can feed to your other units. Okay, then from here, instructions move on to the decode stage. So until this point, everything is happening in order, right? So you're fetching instructions in order. Instructions are moving from the instruction fetch queue into the decode stage in program order. Then here in the decode stage, you are trying to figure out what each instruction is doing, and you are also doing what is called register renaming. Okay, let me explain what this does. So we had introduced the concept of a reorder buffer when we were discussing in-order process and precise exceptions, right? So we said that I need to somehow make sure that everybody writes results into the register file in program order. So as instructions finish, they save the results in this temporary storage called the reorder buffer. Okay, so as instructions come in, they also create an entry for themselves in the reorder buffer. Okay, so as instruction 1 comes in, it says I'll occupy the first entry in the reorder buffer. Instruction 2 occupies the second entry, and so on. Okay, and this helps me know the order in which instructions arrived into the processor, and this helps me confirm that they also leave the pipeline in program order. Okay, so the reorder buffer is just keeping track of the ordering of these instructions. What it also does is it keeps one register worth of storage with every single instruction. Okay, so there's a register over here which is meant to be the temporary storage for the result of that instruction. Okay, so we have essentially said that when instruction 1 finishes, it's going to produce a result, and it's going to write that result into temporary storage T1. Okay, so in my example over here, instruction 1 is supposed to write its result into R1, but we don't do that immediately. Okay, so initially the value is stored in temporary storage T1, and later when it is this instruction's turn to commit, and commit happens in program order, when it is this instruction's turn to commit, it will copy the value from T1 into register R1. Okay, but for now, we'll assume that the result is placed in T1. And instruction 2, when it comes along, is being allocated the second entry, and it's going to save its result in register T2, in temporary register T2, and so on. Okay, so in this example, we've assumed a reorder buffer with 6 entries. Okay, so there are essentially 6 extra registers, T1 through T6. So when I bring instruction 1 into the pipeline, when it goes through the decode and rename stage, I realize that I'm going to place this instruction in entry number 1 over here, which means its result will be put into T1. Okay, so the instruction gets renamed, and this is what the new renamed instruction will look like. And this renamed instruction is placed in a structure called the issue queue. Okay, so the instruction reads from R1 and R2, adds them up, puts the result in T1. Okay, next we fetch instruction number 2, and this will also go through the decode and rename stage. And over here I'll look at what my input operands are. Okay, I need the value R1. This R1 refers to the value produced by this first instruction. Okay, and that value is not sitting in R1 anymore, it is now going to be sitting in T1. So we rename the second instruction accordingly. So R1 gets renamed to T1 because I'm actually referring to the value produced by the first instruction. Then the second operand is R3, right? R3 is going to be in register entry R3. There's no preceding instruction that has renamed R3 to some other temporary storage. Okay, so I just use R3 over here, and the result gets placed in T2. Okay, so this is how instructions get renamed, get placed in the issue queue, and also correspondingly get placed in the reorder buffer. Then we encounter a branch which is reading the value R2. This R2 refers to the value produced by the second instruction, so it gets renamed accordingly, and you're checking the value of T2 before you decide whether to branch or not. I should also mention that this instruction, this branch, does not produce a result that gets stored in a register. Okay, so this temporary storage T3 is going to end up not being used, but you still end up occupying this entry, right? This branch is the third instruction I fetched, so it's going to occupy the third slot in my reorder buffer. But in this case, since I'm not producing a result, that register entry T3 will never will not get used in this case. Okay, it will get used later when you recycle the entries, but we'll get to that later. Then you encounter this fourth instruction, right? So since you encountered a branch, you're going to do some kind of branch prediction, and you're going to guess which way you're going. Accordingly, you've started to fetch instructions from that new branch target, or that expected branch target. Okay, we'll also assume that this architecture does not have branch delay slots. Branch delay slots are typically used in processor pipelines that use the compiler to do most of the scheduling, and we have minimal reliance on the compiler in this case. Okay, so I've done branch prediction. I'm guessing I'm going to a certain branch target, and I'm fetching instructions from there and bringing it in. This instruction then goes through the decode rename stage, occupies instruction 4. It puts its result in temporary storage T4. Its input operands are R1 and R2, which refer to these two values up here. So they get renamed to T1 and T2. Then finally, we deal with the fifth instruction, which is also writing to R1, right? This is the same R1 as this one over here. Okay, but this instruction will essentially get placed in the fifth slot. So it puts its storage in T5, right? So this was a write after write hazard, right? You were writing to R1. You were also writing to R1 over here. This was a write after write hazard, which meant that you could not reorder those two instructions. And we are now alleviating that write after write dependence by saying that the first instruction puts its result in T1 and the second one puts its result in T5. So I've just used different names, and that's the easiest way to avoid these write after write data dependencies. All right, so accordingly, if you look at these two instructions, they seem to have no dependencies, at least no dependence with regard to R1. Okay, so this is how register renaming eliminates write after write hazards. Okay, ultimately, when these instructions commit, this first instruction will write to R1, and later when it's this instruction's turn to commit, it'll write to R1. Okay, so we will never reorder the write into R1 because the commit process makes sure that it goes through instructions in program order, just like we discussed for the in order process. Okay, so the last instruction puts its result in T5. It reads R3, which refers to this value, so it gets renamed to T4. The R2 refers to this value up here, so it gets renamed to T2. Okay, so every instruction as they come in get placed in the reorder buffer and in the issue queue. So again, the process of placing somebody in the reorder buffer is in order. The process of placing someone in the issue queue is also in order, right? So I call this an out of order process, but so far everything has been happening in program order.